In this video, we're going to take a look at this worksheet, and I'm going to go through all the odd questions with you, and then you should take a moment to try and go through every single even question. So, this first set of questions, number 1, says to translate each statement below into explicit conditional form. Identify the given and the conclusion. So, let's just get started right away. Number 1 says, when you don't sleep, you are tired. Well, to put that into conditional form, I need to have if and then. So my given is if you don't sleep, then you'll be tired. Then you are tired. That's it. I took this statement that's just in a regular form that you would say, and I switch it into conditional form. If you don't sleep, then you are tired. Well, the given was no sleep, and the conclusion, when you're given no sleep, the conclusion is that you'll be tired. All right, let's take a look at the second one here. Humans are mammals. In case you don't know what a mammal is an animal that is warm-blooded, has hair, it drinks milk from its mother when it's born. So humans are animals is a statement. It's a true statement. And to put that into conditional form, you would say, if something is human, then it's a mammal. And that's it. I just took the statement, switched it into conditional form. My given was that you are human, and my conclusion from that given is that you are a mammal. Now for the rest of this, I'm going to try and write a little bit neater. Let's take a look at the second set of questions, the truth value set. Now for this, you need to rewrite each statement in the conditional form. Then you need to give a truth value for each. You need to say whether or not it's true or false. For any of them that are false, you need to provide a counterexample to show that it's not true. All right. Given two straight angles, their sum will be 360 degrees. Well, in conditional form, this can be written as if two angles are straight, then the sum will be 360 degrees. This is a true statement, so I don't need to give a counterexample. It's a true statement because if I have two straight angles, that's 180 plus 180, and if I add both of those up together, their sum is always going to be 360. Let's take a look at this next example. Linear pairs are supplementary. So I'll write it as a conditional. If linear pair, then the angles are SUP. I'll do SUP for supplementary. Again, this is going to be a true statement, and that's just by the definition of linear pairs. A linear pair, it's not a counterexample, I'm going to draw it up here. A linear pair are two angles that, when put together, they create a line. Well, if you put them together and they make a line, that means they make 180 degrees, which means that those two angles were supplementary, because supplementary just means two angles that add up to equal 180 degrees. Let's move on to the next odd question, which is number 5. This next odd question, well, we'll keep going. This next question is that right angles measure 90 degrees. So writing it as a conditional, I will say if it's a right angle, which I'll just draw as an angle with that box indicating that it's a right angle, then it's 90 degrees. Well, that is also true because that's just the definition of a right angle. Let's get to finally one that has a counterexample in it. All right, the sum of two primes is never prime. So if you sum two primes, then it's never prime, is what the statement is saying. Finally, I have something that is false, and let's see why. So this is a false statement, and it's false because, well, if I have a couple primes, let me give you just a few. 2, 3, 5, 7, 11. These are all a bunch of primes. Well, this is saying the sum of two primes is never prime. If I'm summing two primes, then the result is never prime. Well, what if I add the primes 2 and 3? 2 plus 3 equals 5. Hey, that's a prime number. This is my counterexample to show that it's a false statement. Now, before we finish this video, I just wanted to go over one more thing with you. Here is a copy, an old copy of the Regions from about almost 2 years ago now. And I just wanted to show you an example of where counterexamples can be useful even if it's not in the question itself. So let's take a look at number 2 over here. So, reading number 2 out. In parallelogram QRST, the diagonal QS is drawn. So first let's start drawing this out. A parallelogram just means a fourgon that has all sides that are parallel. All opposite sides are parallel. So I'll draw out just some sort of parallelogram. Maybe I'll draw a rectangle because a rectangle is a parallelogram. Okay, and I'll draw it as QRST. And then the diagonal QS is drawn. So I'll draw that line QS. All right, which statement must always be true? The only piece of information that we haven't learned yet that you need to know is that triangle QRS is an isosceles triangle. An isosceles triangle is just a triangle of the form where two of the sides are equal in measure to each other. So this side over here is equal and this side over here. That's all the new information you need to know for this question, is what an isosceles triangle is. Well, it's saying that QRS is isosceles. That's not always going to be true, and the way you can show that is by just coming up with a counterexample. Well, here it doesn't necessarily look like it's true, and if I drew a parallelogram that looks like actually, this is a good enough example here. Because this is a rectangle, that means that I know I have a right angle here, and then I have the ability to use the Pythagorean theorem. I can do a squared, this is a, b, and c, and I know that a squared plus b squared equals c squared, and I know that c is always my biggest side, which means that the two sides cannot be the same length over here, so that means that it is not an isosceles triangle. This is a counterexample to it. If I take a look at number 2, it says that triangle STQ is an acute triangle. Even if you don't know what that means, you can probably take a pretty good guess. An acute triangle means it is a triangle that has only acute angles in it. Well, if I drew out a parallelogram like this, this is another example. A parallelogram QRST, it's not saying what it needs to look like, just that it's a parallelogram. Well, these two sides are parallel, these two sides are parallel, and I'll draw out my points, QRST. And if I draw out that line again, the diagonal QS, well, you can see that this corner right here, this angle inside my triangle, STQ? This angle right here inside my triangle, STQ, is not an acute angle. That looks like it's more than 90 degrees, so I can also cross that one off. All I'm doing is I'm taking a look at each statement, each possible answer for my multiple choice question, and I'm saying, is this always true? Is STQ always going to be an acute triangle given what I have over here? If I have a parallelogram and a diagonal QS is drawn, then is that true? Well, I just showed a counterexample. It is not always true. STQ is not always an acute triangle because I just showed you one where it is obtuse. How about that triangle STQ and triangle QRS are, even if you don't know what that symbol means there, which we're going to see next unit, congruent or equivalent or something like that? It looks like, all right, STQ, QRS, they look like they might be equal to each other. Now, one looks like it was reflected over the other one, over a line, but otherwise they look the same. So maybe that could be it. How about number 4? The measure, so line segment QS, again with that weird symbol that kind of means equal, it looks like. At the very least, it looks like an equal sign. We'll learn about that again more later. Well, the line segment QS is equal to line segment QT. Well, let me draw another example of a parallelogram with QS as a diagonal there. So I'll draw a parallelogram. This time I'm going to make it really obvious. This would be a counterexample that I'm going to have. So I'll draw this parallelogram. QRST. And if I take a look, this is a parallelogram, but QT is definitely way smaller than QS, so that means that that is a false statement. I just disproved that with a counterexample. Now, without even knowing all the information in this question, I can answer that it's number 3 just by using a little bit of guesses on that means equal. An acute triangle probably means that it's a triangle with all acute angles. As long as you know the information, you don't need to know all of the little details. And if you can use counterexamples to convince yourself, you can really get pretty darn far in that Regents exam. Let's take a look at one more example like this. All right. We haven't even looked at circles. That's all the way up in Unit 5. In the diagram below of circle O, diameter AB, so this line segment right here, and chord CD, this line segment right here, intersect at point E. Now it's saying if AB is perpendicular to CD, which statement is always true? They have a circle here, but I can draw my own circles out to give myself counterexamples. Well, really you don't need to know any other information here other than maybe that, well, AC, it looks like it's a line segment except it's got that curve. And if you guess that that actually means you're actually going along the edge of the circle. You're looking at that part of the circle. Well, let's see if we can start figuring things out. Will AC always be equal to BD? And my only given is that I've got a circle and that my diameter is perpendicular to some chord. It looks like some line that's going through it. Well, if I draw a circle out like this, and I draw AB as my diameter again, but then I draw CD as a line a little bit further down here, because I just got a diameter and some chord ABCD. Well, now I can see AC is definitely way longer than BD is going to be. So I can cross that off. I just showed AC is not always going to be equal to BD. Maybe if I drew a circle where I had AB and CD being both diameters, AB, and CD, then maybe those two, then maybe those two parts are equal. But if I have an example like this, well, they're not equal. And I'm not being told that they're both diameters. I'm just being told that I have a diameter and something that's called a chord and that they're perpendicular. So this is a counterexample to say, well, at least in this case, that's not true. And that same argument can be used for all the other ones. Let's take a look at number 3 over here. AD is equal to BC. Well, that's the same thing on the opposite side. AD is equal to BC. In this case, this again is a counterexample for that same one. AD is not always going to be equal to BC because look, if I had CD all the way down here, well, AD is definitely a lot bigger than BC. So that one's not true. Number 2 here, BD is going to be equal to or congruent to DA, let's see, BD to DA, same exact problem. DA looks way larger than BD, so my counterexample is still crossing that one off, and let's see if this one makes sense. If this one makes sense, then we've got a pretty good answer here. If BD is congruent to CB, well, it looks like that one is always going to be true. Just by using counterexamples and some inferences and drawing out our own examples, we found out another answer to a regions question without even needing to know all of the terminology, all of the notation about it, just using counterexamples.